The goal of today's lecture is to establish the following formula for the determinant of a matrix. The determinant of a matrix A is equal to the sum over all permutations sigma from the symmetric group Sn, the parity of a permutation sigma times the following product: A1 sigma of 1, A2 sigma of 2 times an sigma of n. So here, where A is a square n by n matrix with entries aij. Recall that we introduced determinants only presenting its properties. For example, explaining how a determinant behaves under elementary row operations. However, so far we did not prove that such a function with such properties really exists. Even though we learned how to compute determinants, we never proved the existence of determinants. So that is the existence of a function that satisfies the declared properties. This is what we are going to do today. Our plan is to first prove that if determinant function exists, it must be given by the above formula. It's here. And the second part of today's class will be proving that the function given by the above formula satisfies all the properties of the determinant. Formally, it's only the second part that we need. So we could have started here, we could have said that let's consider this expression and let's prove that it meets all the properties of the determinant. However, this would be unsatisfactory. It's like pulling a rabbit out of a hat. So we want to show the logic, how can one arrive at this formula. And this is what we will be doing in our first half of the lecture. We're going to see that if one takes the properties of the determinant, then this necessitates that the determinant of a matrix is given exactly by this formula. We're going to start with the notion of permutation transformations. And permutation matrices. Definition. Let sigma be a permutation from symmetric group Sn. A permutation transformation T sigma is a linear transformation that acts on n-dimensional space Fn and with values in the same space, such that on standard basis vectors, it's defined in the following way, that T sigma acting on standard basis vector EI is equal to the standard basis vector E sigma of I. So we know that linear transformations are defined by their values on basis vectors. So if we say what's the value of a linear transformation on basis vectors, this bilinearity completely determines the transformation. And this is exactly what we do here. So here we specify what is the image of each basis vector. So here I goes from 1 to n. And so what we see here, so that this is a very special type of a linear transformation. This transformation just permutes basis vectors. And so thus the name of permutation transformation. And permutation matrix A sigma is the matrix of the permutation transformation T sigma. Let's give an example. So suppose sigma is the following transformation from S4. So suppose 1 goes to 4, 2 goes to 3, 3 goes to 1, and 4 goes to 2. Then, so what does this tell us? What is the permutation transformation T sigma? So this says that T of E1 is equal to E4, T of E2 is equal to E3, T of E3 is equal to E1, and T of E4 is equal to E2. Now let us write down the corresponding permutation matrix. So what is our rule? So the rule is the following. To form the matrix of a linear transformation, we take images of basis vectors and write down their coordinates as columns. So E1 goes to E4. So this gives us the first column of the matrix A sigma. And so E4 as a vector, it's a vector 0, 0, 0, 1. So that is the first column of matrix A sigma. The second column of this matrix is 0, 0, 1, 0. So this is the second column. Then the third column is a vector E1, which is 1, 0, 0, 0. And the last column is the vector E2, so which is 0, 1, 0, 0. So this is the permutation matrix A sigma. So note that each column here has one entry 1, and the remaining entries are all zeros. And the same property holds for the rows. So in each row, we have a single entry 1, and everything else is 0. So this is because our permutation sigma is injective. So we cannot have the same standard basis vector as image of two different basis vectors because of injectivity of permutations. And so this tells us that we cannot have two entries 1 in the same row. We point out that the permutation matrix encodes a permutation. So this is another way how we can possibly write down permutation. So this permutation tells us that 1 goes to 4, 2 goes to 3, 3 goes to 1, and 4 goes to 2. Let us now establish some properties of permutation transformations and permutation matrices. We begin with the following lemma, that if we have two permutations and two permutation transformations, then the composition of T sigma with T mu is equal to permutation transformation that corresponds to the product of sigma and mu. To prove this, let us apply left-hand side and the right-hand side to standard basis vectors. So what is T sigma composition with T mu applied to EI? So this is the same as T sigma applied to T mu of EI. And by the definition of a permutation transformation, so this will be T sigma applied to E mu of I. And then applying this definition once again, we get that this is E of sigma of mu of I. Now, if we take the right-hand side, so T sigma mu applied to EI, then by the same definition, this is E with index sigma mu of I. And we see that we obtain the same result as here. Now, we know that a linear transformation is determined by its values on standard basis vectors. So if two transformations coincide on standard basis vectors, then these two transformations are equal. So from here, we conclude that so composition of T sigma with T mu is indeed the permutation transformation that corresponds to the composition of permutations. As a corollary, we get that the product of permutation matrices A sigma with A mu is equal to the permutation matrix that corresponds to the product sigma mu. To obtain this corollary, we simply take matrices of the transformations on the left-hand side and on the right-hand side. On the right-hand side, the matrix of T sigma mu is the permutation matrix A sigma mu, and on the left, we know that the matrix of the composition is the product of the corresponding matrices, and this gives us the corollary. Let us look at the entries of a permutation matrix. So let A be the permutation matrix A sigma. Then what can we say about the entries of this matrix Aij? So here we can say that Aij is equal to 1 if I is equal to sigma of j, and it's 0 if I is not equal to sigma of j. Now recall that in the notation Aij, I represents the row and j represents the column. So if we take column j, then this column will have a single entry 1, because this column represents the image of Ej, and the image of Ej is E sigma of j. So this means that this position 1 will be only in row sigma of j, and this gives us this formula. So we get 1 if I is equal to sigma of j, and 0 otherwise. Let us come back to this example and let us look at this entry. So this entry here is A41. And what we can say is A41 here is equal to 1. But we note that A41 can be also written as A sigma of 1, 1. Because from this permutation we see that sigma of 1 is equal to 4. And so this is in agreement with what we said here. So Aij is equal to 1 if I is equal to sigma of j. For a given permutation sigma, let us also consider a matrix B or B sigma given by the following formula. So we can say that Bij is equal to 1 if j is equal to sigma of I, and 0 otherwise. Let us understand the relation between the matrix A sigma and B sigma. On one hand, we can easily see that B sigma is nothing but the transpose of the matrix A sigma, because what we have done is we have just switched I and j in the definition of Aij. So we have a transpose. But on the other hand, so this relation that I is equal to sigma of j can also be written as j is equal to sigma inverse of I. And because of this, we get another relation that B sigma is equal to A sigma inverse. From this alternative presentation, we see that if we take A sigma inverse and switch the notations using this little trick, then we will get exactly the matrix B sigma. If we take this corollary about the product of permutation matrices and consider the product of permutation matrices A sigma and A sigma inverse, so then this will give us A sigma times sigma inverse, which is the permutation matrix that corresponds to identity permutation, which can be easily seen as just the identity matrix. And now we get the second corollary, that the inverse of permutation matrix A sigma is equal to the permutation matrix A sigma inverse. But now A sigma inverse is equal to B sigma, which is also equal to A sigma transpose. And so what we get is the following corollary, that the inverse of permutation matrix is the same as the permutation matrix that corresponds to the inverse permutation and is also equal to the transpose of the original permutation matrix. Now, let us look at the determinant of a permutation matrix. We begin with the following observation, that if sigma is a transposition ij, then the corresponding permutation matrix Aij is nothing but the elementary matrix that corresponds to type 3 elementary row operation. So that is the elementary row operation when we switch row I with row j. So if we take identity matrix and switch rows I and j, then we're going to get the matrix that will have in column I, so we'll have 1 in position which is in row j, and in column j we'll have 1 in position which corresponds to row I. So this is the elementary matrix that corresponds to type 3 elementary row operation, and this is also the permutation matrix that corresponds to the transposition ij. We know that applying elementary row operations is equivalent to multiplying by the corresponding elementary matrices on the left. So applying this elementary row operation where we switch row I with row j to some matrix P gives us, as a result, the product of this corresponding elementary matrix with matrix P. So this tells us that the determinant of this product is equal to minus determinant of P, because this is one of the properties of the determinant. So if we switch 2 rows in a matrix, then the determinant switches sign. Now we can prove the following proposition, that the determinant of a permutation matrix A sigma is equal to the parity of a permutation sigma. So this means that this determinant is equal to +1 if sigma is an even permutation and -1 if sigma is odd. So let's give a proof of this. So we know that we can factor any permutation in the product of transpositions. So let's write sigma as tau 1 times tau 2 times tau k, where these tau j's are all transpositions. So we know that we can even assume that these are adjacent transpositions, but here it doesn't matter. We know that the parity of a product of permutations is equal to the product of parities. And so if we have this decomposition of sigma, so this tells us that the parity of sigma is equal to -1 to the power of k, where k is the number of factors in this decomposition. Because we know that each transposition has parity -1, and so then the parity of this product will be -1 to the power of k. On the other hand, so if we take the permutation matrix A sigma, then this decomposition tells us that A sigma can also be factored as A tau 1 times A tau 2 times ... A tau k, and for good measure we can put identity matrix at the end. Then let us look at this formula. So this formula tells us that if we multiply P by a permutation matrix that corresponds to a transposition, then the determinant will switch sign. So here we start with the matrix identity, which has determinant +1, and then we multiply k times by permutation matrices of transpositions. So this means that we are going to switch k times the sign of the determinant. And this tells us that determinant of A sigma is equal to -1 to the power of k, right? So we take identity matrix and then switch sign k times of its determinant. But that's exactly the expression for the parity of sigma. So this is equal to -1 to the power of sigma. And this proves this result, that the determinant of a permutation matrix is equal to the parity of the corresponding permutation. Now we're ready to handle the determinant formula. So let C be an n by n matrix, so which we are going to write in the following way. So we have C11, C12, ... C1n, C21, C22, ... C2n, and Cn1, Cn2, Cnn. So this is the matrix C, and we would like to compute its determinant. We're going to use the properties of the determinant. And in particular, one of the properties is that if we take a row and represent it as a sum of several rows, then we can expand the corresponding determinant in the sum of determinants. What we're going to do is we're going to take row 1, C11, C12, C1n. And we're going to write this row in the following form. We're going to write as C11 and then all zeros, plus 0 C12 and then all zeros, plus all zeros and C1n at the end. And then, so the properties of the determinant tell us that this determinant can be written as a sum. This will be the sum of n determinants, where the first one has C11 and then all zeros, and then everything else is unchanged. And Cn1, ... Cnn. Plus, so we take the expansion of the first row that corresponds to this decomposition. So the last term in this expansion will be the following determinant. So we have all zeros, and the last entry is C1n, and everything else is unchanged. Next, we're going to use another property of the determinant, which says that if a certain row has a common constant multiple, then this constant multiple can be pulled out of this row. And so we see that here the first row has C11 as a constant multiple, and here the first row has C1n as a constant multiple. So this can be written as C11 times determinant of the following matrix. So here we have 1 and then all zeros. Then everything else is unchanged. Plus, well, we have n terms, and the last term will be C1n times determinant of the matrix that has all zeros and then 1 at the end. Next, we're going to apply this idea to the second row of the matrix. So we take the second row, C21, C22, C2n, and we write it as a sum of n rows. So this will be C21 and then all zeros plus ... and so the last of these n rows will be all zeros and C2n. When we do this, we will be also pulling out constant multiples in front of the determinant. So what we're going to get is the following expression. C11 times C21 times determinant of the following matrix. So we have 1, 0, 0, then 1, 0, 0, and then Cn1, ... Cnn. Plus, the next term will be, so C11, so we continue expansion of the first determinant along the second row. So when we take the second entry, so we get C22 times determinant of the matrix 1, 0, 0, then 0, 1, all zeros, and everything else is unchanged. And so we're going now to get n squared terms. And the last term will be C1n times C2n times determinant of the matrix. So 0, 0, 0, 1, 0, 0, 0, 1, and the remaining rows are unchanged. And we can keep going by applying this idea of expansion to each of the n rows. At the end, we're going to get a really huge sum, and we need to find a way how we can write this huge sum in a compact form. So what we see is that in these expansions, we're going to get matrices where each row has a single 1 and 0 elsewhere. Let us consider functions from the set 1, 2, n to itself. And let Fn denotes the set of all such functions. So how many functions can we construct of this type? Well, so let's count. So we need to determine what is f of 1. So we have n possibilities for assigning f of 1. Then we have n possibilities for assigning f of 2, and so on. And we have n possibilities for assigning f of n. And because we are not putting any constraints on the function f, so it could be injective or non-injective, so what we see is that the total number of possibilities is n times n times. So this is n to the power of n. So this is a rather huge number. For a function f of this type, let us define the matrix Bf, or simply matrix B, which has the following entries. So Bij is equal to 1 if j is equal to f of I, and 0 if j is not equal to f of I. So this is the same definition as for the matrix B sigma, only sigma was a bijective function of this type, and f is an arbitrary function of this type. Using these notations, we can write down the formula for the determinant of an n by n matrix in the following way. So we're going to get the sum over all possible functions in Fn. Then we have these products of coefficients where each coefficient comes from a single row. So we're going to get C1 f of 1 times C2 f of 2 Cn f of n times the determinant of a matrix that will have a single one in each row, and that will be precisely the matrix Bf. Now let us analyze this formula. So what happens if the function f is not injective? Well, suppose we have f of s is equal to f of k for s different from k. So then we see that rows number k and s in the matrix Bf are the same. So these two rows will have a single one in position f of s or f of k, which is the same thing. And we know that if a matrix has two equal rows, then its determinant is equal to 0. So from here, we conclude that determinant of Bf is equal to 0. So if the function f is not injective, then the determinant of the corresponding matrix Bf is 0. So this means that in the sum, we can drop all the functions that are not injective. But if here we have a function from the set from 1 to n to the same, and if this function is injective, then this implies that f is also surjective, right? So because if we construct an injective map from the set of n elements to the set of n elements, then all elements should be in the image. So, and then we get that if it's injective and surjective, then this function is bijective. So, which means that f is a permutation. Because this is the definition of a permutation. A permutation is a bijective function from this set to itself. So we see that in this formula we can drop all the terms that correspond to non-injective functions. So what we're going to get is now we're going to get only the sum over all permutations in the group of permutations Sn. And here we get C1 sigma of 1 times ... Cn sigma of n times determinant of the matrix B sigma. But what do we know about the matrix B sigma? So we know that the matrix B sigma is the transpose of the matrix A sigma. And the transpose of the matrix A sigma is the same as the permutation matrix A sigma inverse. And here we know that the determinant of a permutation matrix is the parity of the corresponding permutation. So this is equal to the parity of the permutation sigma inverse. And permutation sigma and sigma inverse have equal parities. So this means that this is -1 to the power of sigma. So the last equality follows from the following fact, that if sigma times sigma inverse is equal to identity, then parity of the product is the product of parities. So we get -1 to the power of sigma times -1 to the power of sigma inverse is equal to the parity of identity permutation, which is +1. And from here, we conclude that these two parities are actually equal. Now we proved the formula announced at the beginning of the class. So the determinant of a matrix C is equal to the sum over sigma in Sn. So this last determinant can be written as the parity of sigma times the product C1 sigma of 1 times C2 sigma of 2 dot 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 Cn sigma of n. So what we proved is that if we have a well-defined functions of the determinant, then this function must be given by this formula. Now, what we're going to do is, now we're going to assume this as a new definition of the determinant. And we're going to show that this function satisfies all the properties of the determinant that we wanted. So what do we mean by a function here? So here we consider determinant as a function on the set of n by n matrices over a field F with values in the field F. And so here indeed, so this formula tells us that if we have a square n by n matrix, so then this produces us a number in the field F. Before we proceed with theoretical discussions, let us see how this formula works for 3 by 3 matrices. Say we want to look at determinant of a 3 by 3 matrix, C11, C12, C13, C21, C22, C23, C31, C32, C33. So here the sum is taken over permutations in the group S3. So this group has 6 permutations. So we have the following permutations. So 1, 2, 3 goes to 1, 2, 3. Then we have a permutation 1, 2, 3 goes to 1, 3, 2. Then we have a permutation 1, 2, 3 goes to 3, 1, 2. Then we have 1, 2, 3 goes to 2, 1, 3. Then we have 1, 2, 3 goes to 2, 3, 1. And finally we have 1, 2, 3 goes to 3, 2, 1. Now, what are the parities of this permutation? So this is an even permutation. So this is a transposition of 2 and 3. This is odd. So this one is a cycle of length 3, so which is even. So that is a transposition of 1 and 2. So this is odd. So this is a cycle of length 3, which is even. And this is a transposition of 1 and 3, so this is odd. And so this formula gives us the following. So we have C11, C22, C33 minus C11, C23, C32 plus C13, C21, C32 minus C12, C21, C33 plus C12, C23, C31 and minus C13, C22, C31. So this is a formula for the determinant of a 3 by 3 matrix. And as we mentioned in our first lecture of the determinant, so here is the way how to memorize these patterns. So we will have 3 products with a positive sign and 3 products with a negative sign. So the terms with the positive sign will be the term where we have a product over the main diagonal, and then 2 triangles with bases that are parallel to the main diagonal. And for negative sign terms, we will have the product over opposite diagonal, and then 2 triangles with bases that are parallel to the opposite diagonal. For 2 by 2 matrices, so this formula becomes really simple, and it says that if we have a 2 by 2 matrix of this form, then so there are only two permutations in S2, identity and a transposition which is odd. And so what we get is, for identity, we get the product A11 times A22. And for the odd transposition, we get negative sign times A12 times A21. Now, let us prove our main result. The function determinant of a matrix given by the sum sigma in Sn minus 1 to the power sigma C1 sigma of 1 dot 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 Cn sigma of n satisfies the required properties. Namely, so 1, additivity in rows. So if we have three matrices A, B, and C such that row number I of matrix A is equal to row number I of matrix B plus row number I of matrix C, and for all other rows, so they are the same in all three matrices. So if J is different from I, so then determinant of A is equal to determinant of B plus determinant of C. So the second property, so if we have two matrices A and B, and row I of matrix A is a constant multiple of row I of matrix B, and all other rows are the same. So for J different from I. So then we have the determinant of the matrix A is K times determinant of the matrix B. 3. If A is obtained from B by switching to rows, so this means that row I of A is equal to row J of B, then row J of A is equal to row I of B, and all other rows are the same. Then we have that determinant switches sign. So determinant of A is equal to minus determinant of B. And finally, property 4 says that determinant of identity matrix must be equal to 1. So what we are required to do is we need to see that if we define determinant according to this formula, then properties 1, 2, 3, and 4 will hold. And the property 4 is the easiest to verify, because if our matrix is the identity matrix, then off-diagonal entries are equal to 0. So this means that we get non-zero products only when for each I and sigma of I are the same. And so this tells us that in this expansion, we will have only one non-zero term. So this will be the term that corresponds to identity permutation. And so what we see is that determinant of identity matrix is going to be plus 1, which is the parity of identity permutation, times the product of diagonal entries. And diagonal entries of identity matrix are all 1. And so what we get is that determinant of identity matrix, according to this formula, is equal to 1. And this property holds. So let us give a proof. So we start with the first additivity property. So let us write down what is determinant of a matrix A. So by our formula, so this is the sum over all permutations sigma in Sn, parity of sigma times A1 sigma of 1, dot 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 A I sigma of I, dot 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 A n sigma of n. Now, in this product, there is only one term from row I. So this is AI sigma of I. And because row I is the sum of row I of matrix B plus row I of matrix C, so we can write that AI sigma of I is equal to BI sigma of I plus CI sigma of I. And then this becomes the sum over sigma in Sn minus 1 to the power of sigma A1 sigma of 1 dot dot dot. Here we have BI sigma of I plus CI sigma of I dot 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 AN sigma of N. So that is equal. So we see that all other rows in matrices A, B, and C are the same. So when we expand this formula using the distributive law, in the first summand we can replace A1 sigma of 1 with B1 sigma of 1, because the row 1 in matrices A and B are the same. So we get the sum sigma in Sn. So here we can put minus 1 to the power of sigma B1 sigma of 1 dot 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 BI sigma of I dot 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 BN sigma of N plus, now we expand this using distributive law, we get sum sigma over Sn. And now we say that first row of matrix A is the same as first row of matrix C. So we get minus 1 to the power of sigma C1 sigma of 1 dot 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 CI sigma of I dot 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 CN sigma of N. And what we see is that this gives us determinant of the matrix B plus determinant of the matrix C. So that's exactly what we had to show. We had to show that determinant of A is equal to determinant of B plus determinant of C if matrices A, B, and C are related in this way. Property 2 I leave for you as an exercise. And so now let us look at property 3. Well, property 2 was about constant multiples of the rows, and property 3 is about switching to rows. So what we have is row I in the matrix A is row J in the matrix B, and row J in matrix A is row I in matrix B, and all other rows are the same. So let us establish the relation between determinants of A and B. So we need to show that these two determinants are different by a sign. So let's start with determinant of A according to our formula. So we get the sum over sigma in Sn minus 1 to the power of sigma A1 sigma of 1 dot 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 AI sigma of I dot 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 AJ sigma of J AN sigma of N. So this equals. Now let us switch to notations of matrix B. So we get the sum sigma in Sn minus 1 to the power of sigma. Now we have row number 1 in matrices A and B are the same. So we get B1 sigma of 1. And now, so row I of matrix A is the same as row J of matrix B. So this means that AI sigma of I is equal to BJ sigma of I dot dot dot. And here we have BI sigma of J dot 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 BN sigma of N. Now at this point, so for each permutation sigma in Sn, consider the permutation mu, which is the product of sigma with transposition ij. Then what we're going to have here is we're going to have that mu of I is equal to what? So first I goes to j, and then j goes to sigma of j. So we get that mu of I is equal to sigma of j. And mu of j is equal to sigma of I. And mu of s is equal to sigma of s. So if s is different from I and j. And if mu and sigma are related in this way, then we can also write sigma as mu times ij. So what we can do is we can switch from summation in sigma to summation in mu. So we get summation in mu in Sn. So now we have -1 to, well, sigma is mu times ij. So we have mu times the transposition ij. And so here we have b1. Well, sigma of 1 is the same as mu of 1. Dot, dot, dot. So now we have bj. And sigma of I is the same as mu of j. Mu of j. Dot, dot, dot. So then we have bi. And sigma of j is equal to mu of I. Dot, dot, dot. bn mu of n. Now, here, so what we know is we know that the parity of the product mu times the transposition ij is equal to the product of parities. It's parity of mu times the parity of the transposition, which is equal to -1. So what we get here is we get -1 times the sum mu in Sn -1 to the power of mu b1 mu of 1 dot 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 bn mu of n, and this is equal to negative determinant of b. And that's exactly what we had to establish in this property. And since property 4 about determinant of identity matrix is already established, so this completes the proof of this theorem. And there is one more theorem that we want to prove today that says that determinant of the transpose of a matrix is equal to the determinant of the original matrix. And so let's prove this. So let B be the transpose of the matrix A. Then we can write determinant of B according to our formula. So this is the sum sigma in Sn, parity of sigma times b1 sigma of 1 dot 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 bn sigma of n. But what is the relation between the transpose matrix and the original matrix? So the relation is that bij is the same as aji. So this sum then can be written as the sum sigma in Sn, and we have -1 to the power of sigma a sigma of 1 1 dot 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 a sigma of n n. Now there is another way of writing this formula more compactly. So we can write that this is the sum over sigma in Sn -1 to the power of sigma times the product, right? So this is the notation same as the sum notation, only for the product. So this is Greek capital letter pi. So we have the product over I goes from 1 to n, and here we have a sigma of I. Now, if we denote sigma of I by j, then here we will have that I is equal to sigma inverse of j. And so now we can write this as the sum sigma in Sn. We have -1 to the power of sigma. So the product j now goes from 1 to n. Now sigma of I is equal to j, and I is equal to sigma inverse of j. And now we just let mu be sigma inverse. And so we get the sum over mu in Sn. We have minus 1. Well, sigma is now mu inverse. And here we have the product j goes from 1 to n, aj mu of j. And since we know that minus 1, the parity of mu inverse, is the same as the parity of mu, then what we have here is just the formula for determinant of A. And in this way, we proved that the determinant of the transpose of a matrix A and determinant of A are equal. Let us take a second look at this formula for the determinant. So this formula is a sum of products, and the number of summands is equal to the size of the group of permutations, which is n factorial. And n factorial is a very large number even for modest values of n. So this tells us that this formula becomes impractical when n is fairly large. We use this formula as a computational tool only for n equals 2 or 3. For n equals 4, so 4 factorial is equal to 24, and this is already not very practical. We'll have a sum of 24 terms. And for n equals 5, so this sum will contain 120 terms. For n greater than 3, if we need to compute the determinant, we use the method of elementary row operations. So we use elementary row operations to evaluate the determinant. So that is more computationally efficient than using this formula. There are also additional methods that we will discuss in the next lecture that will allow us to compute determinants in special situations. Even though this formula may be not practical as a computational tool for large matrices, nonetheless, this formula is very important as a theoretical result.